first, why we are using steel? Now steel you can use to create any shape, right? You can create in smaller length, slice it, make it longer. You can, it's very sustainable when we are talking about carbon neutral things and sustainable things. It's very sustainable. You are using it today, you can dismantle it tomorrow, recycle it, it can be reused, right? Then the structure can be disassembled. You can, suppose you want this auditorium, if you want to expand the span or something, you can just weld additional plates so that it can be strengthened. So steel is a very versatile material, but it has only 2 or 3 problems. The problem is corrosion, how to take care of that. So we'll just discuss briefly about that. And fire, right? And the cost. But cost, the thing is that once you take into account the life cycle cost or and the sustainable that it can be reused, then you'll find that the cost comes down. Okay, now when we come to composite construction, what are the design methodologies followed by our various codes? IS 800, it follows SLS, serviceability limit state, ultimate limit state, and fatigue. Same thing is followed in IS 11384. And when we come to IRC codes, IRC 22 is for composite and 24 is for steel. So there also it is both ULS, SLS and fatigue. But when you come to IRS code, that is Indian Railway Standards, it still follows the working stress method. And the fatigue, of course, is there. So it is still follows the working stress method, and that may be probably one of the reasons why you find some of the old railway bridges which were designed for meter gauge are still working with for the 25-ton loading today. And the latest is the Euro codes, Euro code 3 and Euro code 4, which are for steel and for composite construction. Okay, now what are the types of steel? Basically governed by IS 2062. It gives out the various categories of steel which are available. So that gradation is shown on the right side, this table here. And the types of steel, you know, when you say steel category type A, type B, type B0, what are they, you know, and where they are to be used? So very simple, this one is that A, I'll just go to one, yeah. So this is very simple, you know, you can understand where the various types of steels are to be used. So you have, India, we have divided it into 3 zones, depending on the temperature zone, right? So zone 1 is where the shade temperature is greater than 0. Zone 2 is the shade temperature is from 0 to minus 17, and zone 3 is the shade temperature is less than minus 18. So in these zones, specifically for the users in bridges, and even this is applicable for whenever you are using for girders for machine foundations also, because there are also due to fatigue, it becomes fracture critical. So there, depending on the zone, so for example, if it is in zone 1, you are using say grade 250, 275 or 300, you can use BR. Grade BR, right? If you are using grade 350, then you have to, that also BR is applicable. If you are using higher, say grade 410, then you can use only grade C. Or if you are using grade E40, that is 450, higher strength steel, then you can use only type C. These are the criteria based on the fracture. So for normal buildings, these may not matter, but if you are building industrial buildings where you are having fatigue loading, machine loading is there, this will become more critical. So now, what is the difference between a composite and non-composite? Okay, suppose you have 2 beams, you know, B and H. You keep one below the other, you apply the load on them, what happens? If it is behaving individually, you'll have, this will be the shear diagram, bending moment diagram, and this is a shear stress diagram. But if it is made composite, then what happens is the stress, you observe that it will become half, right? The shear stress will remain the same because the depth is same. The same depth is taking the shear, but your bending stress is reduced drastically. So now here, suppose you don't make it composite, then what happens is, once it bends, one will slip over the other, right? So that there is no composite action. But if you provide shear connectors and you connect it together so that there is no slip, then what will happen is, here you can see, this is with very high slip and this is with very low slip, right? So the lower the slip, then the better will be the composite action. So this is just for your stress strain as you know, concrete, it just goes and then it breaks away, but steel you have, for normally what we use, this is a structural steel, it will have a very long deformation, you know, even at yield stress, you had very long deformation is possible in that. So these two properties, when we are combining, we are getting very good property for the composite material. Now, a material can be said to be truly composite only if it has been proper shear connection, shear connection, so that one will not slip over the other. So these are the various types of shear connectors you can have. And the most commonly used one is the one on the right, which is the shear studs. Okay. Now in this one, just one point I want to make. There are what you call rigid and flexible shear connectors. The rigid one are not very effective in fatigue. The flexible ones are very effective in fatigue. And if I go to here, you will find our shear stud and even this channel connector, what we have. They come in the category of flexible connectors, whereas the bar connectors and all, because the connection is very rigid, it comes under rigid connection. Okay, this is a small capacity comparison I'm showing. You have a composite beam, okay, and the overall depth is 560. So here I'm considering that whatever it is, the design load is, that is 100% it is taking. So suppose I'm doing it non-composite, what happens without shear connectors? So a case is that you have to increase the depth, right? So from 560 it increases to 710, so that your load capacity is the same, but your steel weight increases to 59%. Your construction height, that depth increases by 27%, and your stiffness reduces from 100% stiffness, you are getting only 72% stiffness. Now what happens if you want to restrict the depth? Almost you want to maintain the same depth, so you are using a standard section here, that's why it's 520. So load capacity is, again, I want to maintain the same load capacity, but the steel weight has gone up 214%. So you can see here how effective and how efficient the composite section can be. Now, one more thing in composite construction is whether you are doing a shored construction or unshored connection, right? Shoring is you are propping up. So when you are putting a steel beam and I'm supporting the steel beam, when I'm pouring the concrete, it's a propped construction. So the capacity for that will be higher, rather than suppose I'm having only a beam and I pour concrete on that without any support below that. What will happen is that the steel will take additional load of the concrete. So that is unpropped. So unpropped will generally have slightly higher capacity. So this is just the stress distribution, elastic distribution. One is where you have the elastic, the neutral axis is within the concrete, and the other case is the neutral axis is inside the web of the steel. The same thing when we are doing for the plastic capacity check, this is the plastic moment stress distribution. So now when we use this, we always use decking sheet. Advantage of decking sheet is that, the dimples you see in this one or here, the embossment and all, they are basically acting as shear connectors. It is not it is connect with the concrete, so that there is a connection between the decking sheet and the concrete. So whichever decking sheet you are purchasing, the manufacturer will be getting this kind of tables where it is very clear as to, depending on whatever thickness of the concrete slab you are putting on top, how much span you are providing, and for that span what will be the total load which can take. So whether it needs to be propped as given here, or it is without propped, that case given. So those tables are available, I think, with all the manufacturers of decking sheet. So now next is, when you are welding the deck sheet, so how it is to be welded? What is called, this is puddle weld or spot weld, or what you can give the shear connectors, which we are giving here, right? Now, how do you keep this on the girders? Well, our code, it specifies how much it should be, So if you see here, LBS, so minimum bearing on steel, it should be 50 mm, right? 50 mm should be the minimum bearing of the deck sheet onto the steel or concrete girder where you are providing. And now for studs, the puddle weld what you saw was simple, but for studs, it is not a simple welding. So for studs, you require a special welding process. The entire welding machine comes along with this process, and the welding process is done so that you have a proper connection. Next, you have done the shear connection. So what happens is, now there will be interface shear, right? So there will be one, this is the interface shear one, because this is the steel beam or precast beam, and you have the concrete slab on top. And the second is, it can fail on this side. So this 2-2 will be on this side. So this entire thing can act as a section, but it can fail on this section. So we have to check for both the cases at a section 1-1 and 2-2. And if you refer the IRC code, they have given very clearly how the modeling is done as a truss, shear truss, and the truss angle, how it behaves. And now just a small thing on how the deck sheet and deck slab action occurs. The basically is that the capacity depends only when the slip is less than 2 to 3 mm. If it is more than that, it means it has slipped, so your capacity will come down. So the slip capacity should be relative slip between those two at ultimate state should be less than 2 to 3 mm. So in practice, this will not occur. Generally, we'll be having much lower because ultimate load is generally not encountered. Next criteria is the deflections. So how are the deflections taken care? So if you refer our IS 11384, it gives you some criteria that, first thing is it should be less than 1/10 of the depth of the composite slab. This is to prevent the ponding effect. The second is it should be less than L by 180 for the wet concrete. And for the once the entire slab becomes composite, it is L by 350. Right? So similar kind of guidance is given in Euro code, that is L by 180 or 20 mm. And for composite, once the slab becomes composite, it should not exceed 250 or 350. And if you have been to seen Steel Construction Institute website, they have got again very beautiful handbooks are there, very detailed. So there they have given very detailed flow chart, how the design flow chart is to be done, whether once you are designing, and you have chosen the preliminary sizes, are you going by composite section, uncomposite, propped, unpropped, how it is to be done. The complete design guideline is given. And similarly, along with that, even the flow chart is given for the construction also, at what stage it is to be done. And one most important thing you see here is, they need a system that is fail-safe, that once you have your columns and all, and the beams are in place, it should not sway. The system should be fail-safe. So that is one of the most important criteria during construction. Next is when we come to the design, we look at the material factors of safety. So these are the material factor of safety as per IRC 22 and IRC, our IS code. So they are given for various, whether the resistance is to bending or to buckling or which state we are doing. And you are checking for bolt or rivets or welding. And when you come to our composite code 11384, again they have given very detailed factors for limit state and for serviceability state. So here, if you see, even for reinforcement and for concrete and shear connectors also, the limit state factors are given. Then section classification, I will not discuss because Dr. Sanat Kumar had already explained it in detail. What are the 4 classes of this one? So normally when we design, our design should be for class 1, class 2 or class 3. Because if we are designing class 4, what we have to do is we have to reduce this in the middle so that we come back to at least class 3 level. Just to give you an example, suppose you are having a 16 mm thick web for 2 meter depth. So your length to thickness ratio is 125, right? And allowable is 126. So it is safe. Suppose you are using a 12 mm web, then what happens? And 2 meter depth, the ratio is 166, but you need to reduce it to at least 126. So how much you need to reduce from that? So 4 out of 2000, 1512 is the value for 126. So you need to reduce 488 mm. So 488, where you will reduce this is the portion where you are reducing the 488 mm. That will be above the neutral axis, not in the tensile zone, but in the compressive zone. Okay, next is the effective slab width of the deck slab. So deck slab effective slab is generally L by 4 or L by 8 if it is the outer one, but it shall not exceed the beam spacings. So this is as per the IRC code and this is as per our IS 11384. So both the meanings are same. Only thing here they have added that this B0, which is the spacing between the 2 shear connectors, that also can be added. Next, I am just going to go for, this is for the plate girders for mainly bridges. So design of plate girder, the depth should be more than L by 25. So whatever is the span, so your depth cannot be less than 1 L by 25th of that. Then deflection is given as L by 600. For DL plus SIDL plus live load, and only due to live load it should not deflect more than L by 800. This is for the bridges, but for our normal buildings it is L by 350, so much more lenience is given there. L by 325, 350, whatever is there. So I'll just give you a very small example for a span of 25 meter bridge, which is a 24 meter center to center bearing is there, and the girder spacings are at every 3 meters. The overall width of the carriageway is 12 meters. So I'll just go through very briefly. Just before that, one thing is when we are designing in composite, 2 things we have to remember. In concrete, you have the creep and shrinkage. So that's why we have to take the long term and the short term properties. So how do you take the long term and short term properties for the composite section is be effective, you reduce or increase depending on that. So your modulus, right? Long-term modulus is 15 and short-term modulus is 7.5 minimum. If you are having something more than that, as per the design, you can take that. But minimum it should be 7.5 and 15. So whatever is the effective width, divide by modular ratio, you will get the effective section. So here we have taken E350 and concrete M30. So I'll just go. This is the cross section. So you can see 1, 2, 3, 4 girders. And this is at the near bracings. And this is at the end section where you have the end diaphragm. And this is the section adopted. Okay, so these are the, in plan you can see the 4 girders. And this is the elevation where the splices are shown and that. So now here the depth required is 24 meter by 25. So 960 mm is required. But their depth was not a criteria at all. And the contractor wanted it efficient section. So we went for total depth of 1545. That is 1500 was just the depth of the web. And then we have the top flange and bottom flange of 20 mm and 25 mm. So these are the properties. So this is the only girder only property, and this is with the girder with the short term composite property and long term composite property. So for the analysis procedure, what do you do? So first thing is you have your self weight plus that is the girder weight, and you have the weight of the concrete on top. Okay, so that is without prop. So what you do is if you are using it with prop, then you will have to use the long-term composite property. If it is without prop, then it is the properties is only of I girder. Then when you apply SIDL will be on the composite long-term property, and live load will be applied for the short-term property. So these are the things you have to bear in mind when you are designing the thing. So the deflection of plate girder, as I explained earlier, L by 600 for all the loads combined, and only L by 800 for live load. So here you can just see what are the moments we got moments and shear at support and midspan. I'll just share the presentation with the organizers so that they can email it to you guys. So just total, these are the moment at midspan, and this is the shear mainly at support. And for that, the shear is carried by only the web of the steel girder. So again, for that, the shear check is given. Here, the procedure and the clause which I have mentioned is as per IRC 24, but the same formula is there in our IS 800 also. So one thing we have to ensure is that should the shear coming is less than 0.6 times the capacity. So this is the overall shear check. Then once the shear check is done, we have to do the buckling check also. So for buckling check, if the depth to thickness ratio, so it should be within this limit, then buckling check is required or not required. So here the clauses are given. So based on this, as for our case, those stiffeners are provided, and spacing should be this one, buckling check is required. So shear buckling, we are doing detailed here. So they have two methods are there for shear buckling. One is the simple post-critical method, and the second is the tension field method. So you check by both the methods, and we find that the section is safe. Then next is the moment capacity. So moment capacity is at the service stage. So here the ultimate moment, first you have to check out where your neutral axis is coming, whether it is in the deck slab, or it is in the top flange of the beam, or it is in the web. So for that, the values are given, how it is to be calculated, it is to be checked. So once we check, in our case, we find that the neutral axis is within the steel flange. So based on that, the capacity, plastic moment is 11,000 kilonewton in our case, and the ultimate moment which is coming is around 7,000. So that is safe. So next is the fatigue. So fatigue will come not for normal buildings because you won't have so much of fatigue loading on that. But for the machines it will come, and for bridges it will be there. So because this is a built up section, so the category detail is 92 as per the code. So if you see here for category detail 92, and you have to design it for minimum of 2 million cycles per year, and bridge life is 100 years. So we are designing for 2 into 10 raised to 8. So here if you see 2 into 10 raised to 8, and for this detail category 92, it comes somewhere here. So for that, if you see, it comes to around 72. So 72 MPa with 1.25 factor of safety, 57.6 MPa is the only allowable stress for fatigue. And with the fatigue loading applied, our actual stress comes to 50.2. Hence, it is safe in fatigue. Next is the shear connector design. So shear connector, you will have to check for ULS case, and again for fatigue case, and ultimate shear. So how do you do is, you first calculate what is the longitudinal shear. I had shown you two shear planes, right? So this is the first shear plane we are checking at top of the flange. So the capacity of the shear studs, because here we are giving the shear stud, this is the capacity is given in the code, and for channel this is the capacity. So here for due to dead load dead load of the slab, then due to SIDL, that is wearing coat and crash barrier, and due to live load. So we calculate what is the total shear flow on that. So this is the total ULS longitudinal shear to be resisted by the shear connectors. So the code gives us the capacity of the shear connectors, right? So for example, we are using a 25 dia shear connector, and minimum height is 100 mm. For M30 grade, it is around 125. So here also again it is given very detailed. Again, this is not for the fatigue. That was for ultimate. This is for fatigue case. So this is for 2 into 10 raised to 6. That is 2 million cycles. The capacity is given. So now what we do is we check again for our criteria. What is the thing? So first we check for fatigue, then for strength, and then for ultimate shear. So we check based on that what is the thing required, how many shear connectors are required, what is the spacing required. So if you see here, we require at least 3 numbers, 3 rows, and at 80 mm center to center. So now next is the stress check.
Non-composite case, the depth of the beam is higher. So how the stiffness is reduced, sir?
Talking about the overall stiffness, right? In composite section, the stiffness is stiffness of the I-beam plus the deck slab. Okay. Whereas when you go for just the I-beam, you are having only the stiffness of the I-beam, and therefore the stiffness is much lesser. No, when in non-composite there is no shear connector, so it is not acting as composite, right? So the stiffness will be only the stiffness of the I-girder only. Because deck slab, what you are putting on top is a load onto the thing. Now the basic difference between composite and non-composite is that composite will be very efficient because you are providing shear connectors. Suppose you are not providing shear connectors and you are using the same I-beam, what happens is that I-beam will behave independently. So whatever load is coming, just that I-beam is taking. Now by providing concrete on top and providing shear connectors, I am utilizing the property of the concrete also. So my section is, instead of whatever say 500 mm beam is there and 150 mm concrete is there, my overall section becomes 500 plus 150. So 650 is the overall depth now.
Yes, sir, my question is, you are saying that we can use the CRS steel also. I think in 2062 grade, CRS is not coming. Is there any manufacturer who is producing the CRS steel?
No. See now stainless steel also has come, and that is there in many bridges, even in India, they are being built with stainless steel, right? So that is also nothing but corrosion resistant steel, right? The issue with corrosion resistant steel, CRS, is it has only some amount of resistance. It is not as durable as stainless steel. So it depends on the environment where you are using which kind of thing. And in Karnataka, even in the PWD SR, now they have added the stainless steel, structural steel and stainless steel reinforcement. Both are added. And they have made it mandatory that in all the coastal areas, within 15 to 20 kilometers from the coast, you have to mandatorily use stainless steel.
What are the treatment plants? We are using the stainless steel, and building reinforcement steel also we are using the stainless steel, sir.
No,
you are saying that for the bridges also we can use that?
No, for bridges it is mandatory. Buildings, see, generally the thing is very simple. Buildings you are normally designing for 50 years or 70 years, not more than that. Bridges, your target is 100 years. In fact, July 30-31, we are having a 2-day conference in Bangalore by ING IABSC. There the topic is going to be 200 years, how to make the life of bridges 200 years. And we are going to be discussing about some of the bridges which are already constructed, existing on say in Japan and Finland and Korea, where they have designed it for 200-year lifestyle. It is designed for 200 years.
We can microalloy the steel and can get the corrosion resistance also, like nickel and chromium, and we can get the microalloying and we can get the corrosion resistance.
Yeah, that's what chromium and this one, what is that, molybdenum and all that composition, you change it, you can make it.
Hello sir, this is Durga Prasad from Kakinada Center. In one of the slide, you have mentioned that the design is failed in deflection before applying the camber. After applying the camber, the design is got success. What is the mechanism, sir?
No. It is not that it is failing. See, the deflection check, what we have is, it sags too much. You know, it will look unpleasant. You know, somebody who is seeing, it will give you a feeling of that the structure is unsafe. Though the structure is structurally safe, just because the sagging is more, it will appear that. So to take care of that sagging, what we give is, we give pre-camber. Pre-camber is when I am assembling the girder, instead of making the girder straight, I will make the girder in a parabolic fashion. So you cannot theoretically actually make it in parabolic fashion, but what we do is, suppose we have 3 pieces, 2 pieces I put like this, 1 piece is like this. So it will come in that shape, so that when the load comes on top and it deflects, it will come to a flat shape. It will not sag too much. Please.
One is the temperature, the thickness that you provided, that we govern the thickness with. What is the temperature consideration of the fire?
No, see, the thing is very simple. What I showed you, that was from SCI, as I told you.
Correct.
Steel Construction Institute. Okay, they have done extensive study, and they have found out, suppose on top of your decking sheet, the concrete is just 10 mm. So if it is 10 mm and is exposed to fire, what happens after 1 hour? What happens after 2 hours? What happens up to 4 hours? What will be the temperature which the steel will face, bottom steel will face? Right, so for 10 mm, 20 mm, 100 mm they have given. So you can see, the thing is that at 800 degrees, your steel will lose all the strength. It will just begin to melt. So you cannot have anything. So your temperature you have to keep within 800. So they have given all that table, that what thickness you have, and that thickness, suppose you have designed this building, for example, for 2 hour fire rating. For 2 hours it will be safe. What happens 3rd hour? Temperature will increase, right? 4th hour, temperature will further increase. Maybe it may cross to the steel melting point. So at 800, the steel will lose the total strength. So that is how they have done the checking. So that table basically, 1 second, if you can, suppose I am having, for example, 200 mm concrete slab. So for the first 10 mm, what will happen is, in half an hour of fire, I am using, say, normal weight concrete. It will reach 470. Next 20 mm, it will reach 350, 340. Next, so up to 100 mm, if it is 100, it will be 60 only there, right? So the amount of concrete cover you have for the steel, that will be this one. So suppose you come to 4 hours. So in 4 hours, what happens is, on the concrete, with normal weight, it will reach almost 360 degrees there. So suppose you are lesser than that. Suppose you are, this can be applicable for your normal reinforcement, where your cover is only 15 to 20 mm. Yeah. Covered in the deck slab. So here what happens at 4 hours is that it will fail.
Yes, this I understand, because the lesser the thickness, the higher is the temperature. So we are reaching the threshold.
Right.
But in the other slide, where we have this guiding table which shows the FRL, for 1 hour fire rating, this much is the thickness.
Oh, okay.
For 2 hour fire rating, this much is the thickness, right? So
this one, okay.
Yeah. So this is to what temperature? Yeah.
It may be, one thing what I think, this may be for 40 to 50 mm, because that is the nominal cover you give.
What about the temperature? So this is a threshold temperature.
I can just recheck, because this is from a company specific like ComFloor. So there they give this kind of rating, that you have, this is the deck thickness and this is the mesh reinforcement. So for 1 hour, this is for this span, this much of load you can take.
Yes.
So that I think, I don't think that is linked to the temperature. It may be linked to the deflection also. Once it deflects too much, then also it becomes unsafe. So it may be referring to that.
So the element under consideration is a deck.
It is the
steel
deck slab.
deck.
It is the deck slab.
Deck slab.
Yes. Deck slab with profile.
With the
profile deck slab. Yes.
Okay. So the next question was you had this shear flow happening in 2 planes. Mm-hmm. So one is between the slab and the girder. Yeah. And the other one is the engagement of the flange.
Yeah, within the slab. Yeah.
Yes. So the plane 2 that you showed.
Yes.
So normally our code says, you showed the B effective, the flange width, effective flange width.
Yeah.
That we can consider. So by just considering the effective flange width, are we okay in plane 2 of shear flow calculation?
No. That shear flow, you have to check for this. What will be the shear flows? I mean, that formula no? What we have.
Yeah, but
V
that
y by I, whatever is there.
But that will be for the bending.
No. Listen. V I by I is the standard formula for your shear flow.
Yeah.
So now here, what I am taking I, and what is my this one? If I am considering top of the steel flange, my I and Y are different. And what I am considering, if I consider just the concrete on top of the flange, okay, that much entire area I am considering, my I and Y is different. So what I am checking is just the shear in concrete. Plane 2. Plane 2 is basically your shear in concrete. So your minimum reinforcement should be such that concrete should not shear.
Right.
Because I have ensured that, I've got put very good shear connectors so that my concrete and steel is in contact, it will not fail. But suppose you have failed to provide the minimum reinforcement required for concrete and that load comes, it will shear, that concrete will shear here along this. So here the checking is for concrete, not for steel.